Think back to your college or high school physics class. Do you remember Ohm's law? It had voltage and current and resistance. That's what I want to talk about, electrical resistance of the ground. Now, resistance varies with the size of the resistor, so it's not really useful in mapping. So we use resistivity, which takes into account the size and the geometry of our measurement. Essentially what we do is we hook up a battery to two metal stakes driven into the ground to create an electric current. Then we measure voltage between two other stakes. We do a simple little calculation, come up with resistivity. Occasionally, we compete with other practitioners. Now, resistivity is black box, but it is based on physical principles. It does have reproducible results. When we do resistivity measurements, we inject electricity into the ground. We try really hard not to shock people or animals. It does sometimes happen, however. We're not the only ones in an agricultural area that create pulsed electric fields. So we have to avoid areas with electric fences, electric power lines, buried metal pipes, and sewers. I'm told that there's a really similar setup that's used to drive worms up to the ground surface. But I have never personally noticed any unusual animal behavior associated with any of our surveys. And we have been doing these surveys at the State Geological Survey now for over 70 years. And in that time, we've used many different types of field equipment, kinds of portability and such. Today, however, we use digital instruments with multiple receiving channels that automatically switch through hundreds of measurements on an array of electrodes so that we can create a 2D image of the subsurface. Resistivity is sensitive to several different useful properties. For instance, we often take advantage of the contrast in resistivity between clay, which has a really low resistivity, and sand that has a high resistivity. It was initially used to locate mineral deposits because it's very sensitive to the ionic content of groundwater. This graph, for instance, shows the strong relationship between chloride concentration and resistivity, which is a property that's extremely useful in environmental applications, tracing leachate plumes. Here's an application at a landfill. Similar research is done on coastal areas looking for fresh and salt water. When a dead body decomposes, it produces some really nasty juices that are highly conductive. Resistivity can be used to locate a buried body by mapping the resistivity of those fluids. Resistivity is also especially good at locating sand and gravel deposits that are buried within glacial till. It's been our bread and butter application for water resource mapping at the State Geological Survey. The result of 2D profiling is an electrical model of the subsurface. For instance, in these ridges, we can image the sand, here shown as warm colors, distinguish it from clay, shown in cool colors. Resistivity is a really well-known application for mapping archaeological sites, looking for hearts, walls, foundations, implements, all of which have a different resistivity signature from the soil. Combining resistivity images with images of other geophysical methods, such as seismic reflection profiling, which we show here, is one new way that we can get more bang for the buck from our geophysics. With our new multi-channel high-speed receivers, we're able to tow a resistivity cable from behind a boat and acquire nearly continuous profiles of sub-bottom sediments. Electromagnetic induction, it's a variation on resistivity, and it can be done from the air. Now, although they're expensive, airborne surveys have the potential to provide continuous, high-resolution 3D images of the subsurface. I've really only had a chance to scratch the surface of applications of resistivity. Perhaps you can think of some others that you want to use in your research, and let me know. Maybe we can come up with a collaboration. Thank you.